Okay, hello, class. This was the homework on partitions, partition numbers, Stirling numbers of the second kind, and occupancy problems in general. Part of this homework was relatively straightforward, but part of it I think was really hard. So let's do the easy part first, so we kind of get comfortable with all these things. All of 8 through 20, now that may have seemed like a lot at the time, but actually all of them just involve reading, thinking for a minute, and then just writing something down. So maybe they take 2 minutes each, 1 minute each, 3 minutes each, I don't know. We're going to just do them all. Well, I assigned them all, and we're going to just do them all right now. So let's go. I'll read them aloud, and well, we can't discuss them, so that's kind of annoying, and I think this is one of the most fun lessons to do. There's a fun homework also to go over in class live, so that's really sad. Anyway, here we go. Number 8 says, I have a large bag of identical candy bars. 4 young trick-or-treaters have just knocked on my door and are holding their bags out for some candy. If I grab 6 candy bars from my bowl, in how many ways can I distribute all 6 of them? Okay, so you imagine the 4 trick-or-treaters have all held out their bags, and your job is to just put 6 candy bars, which are all identical, the candy bars, into those 4 bags in any way you choose. You might even just like have them, you know, put out their bags, and you're just going to throw the candy bars in the general direction and see where they fall. You know, there are 2 ways to interpret this problem. The mean, you know, like whatever, old Mr. McGregor, I don't care about the stupid kids in the neighborhood, way would be that I don't even care if some kid doesn't get a candy bar from me at all, then so be it. In other words, this is a objects indistinguishable, because the candy bars are all exactly the same. Containers, distinguishable because the bags are all being held by each of the 4 different people who are presumably dressed differently for Halloween. And there are 2 options, Gossip doesn't say, which we should follow for whether empty containers are permitted. If empty containers are permitted, so that you could just not give a kid a candy bar at all, then this becomes just a classic stars and bars problem. I have 6 I have 6 candies, and I have 4 bags, and so what do? I imagine the 4 bags being divided up with 3 vertical lines, and then I just place my 6 candies any which way I want to in between. And so that makes a, such as that one, that makes a string of length 6 plus 3 equals 9, and so that's 9 choose 3 according to the stars and bars method, a way to do that. If, on the other hand, we want to be like a nice person in which, even though we're giving out the exact same kind of candy to every kid, the bags held by the various members in the house are all distinguishable from each other, but if we're not allowed to not give someone a candy, or we must give each kid a candy, well then that just becomes easier, right? Because now you have your 6 candy bars, you give one to all 4 kids, and now one to each of the 4 kids, and now you just have 2 candy bars left, and now you just do a stars and bars with those 2 last candies. And so it's the same setup, and now it's just we have just 2 stars to distribute among the 3 vertical lines. So that's a string of length 5, and so it's 5 choose 2. Alright, point is, problem 8 was a little ambiguous, and we already knew how to do these problems. We just didn't call them at the moment occupancy problems, or discuss them from this abstract perspective of objects and containers and distinguishability, but this is an old problem that we saw from chapter 5. Okay, we push on. Number 9. Number 9 says, Jody has 12 identical boxes of Girl Scout cookies. She plans to sell them all to relatives. If she has 6 candidate relatives, in how many ways can she unload the cookies?
You may assume that some relatives may decline her offer, but that all the boxes will be sold. Okay, so basically, how many different ways are there for Jody to get 6 different relatives to buy her 12 boxes of Girl Scout cookies? Well, when you think about it that way, this is again just the stars and bars problem. You have the 6 relatives are divided up by 5 vertical lines separating the relatives into the 6 relatives, and now you're just unloading, as Gossett says, your 12 boxes of Girl Scout cookies are the stars in and amongst those 5 vertical lines, giving you 12 plus 5 equals 17 characters, and so there are 17 choose 12 ways to do this. Well, what is this? This is an objects indistinguishable, because the Girl Scout cookies are all the same, identical boxes. Containers are distinguishable because the relatives who are going to be receiving the Girl Scout cookies are different from each other. The empty set is certainly permitted because, as he says, a relative may decline the offer. Okay, good. So still nothing new. 10. What's up with 10? 10 says, a technology company is moving to a new building with an excess of space. The company has 11 programmers on staff. If the new building contains 2 identical office suites, each large enough to hold up to 10 programmers, in how many ways can the programmers be assigned to suites? Okay, oh man. Well, there are these programmers. There are 10 programmers. No, sorry, 11 programmers. 11 programmers. There are 2 rooms. And the 2 rooms, or office suites, I'll just say rooms, are completely indistinguishable. And, let's assume there are no windows, even the view isn't different, the rooms are exactly the same. In other words, it doesn't matter which room you happen to be in. The only thing that can distinguish one room from another is the people that are in the room. So this problem essentially is asking us, hey, if you have 11 programmers, how many ways can the programmers be assigned to suites is equivalent to how many ways can you divide the programmers up into groups, because the only thing that determines the difference between 2 different ways of doing it is who's in the room with you. Okay, well, the programmers, they are people too, so they are actual distinguishable people. And so what we have is a, well, hold on, I gotta be a little bit careful. This is a objects distinguishable, because the programmers are the objects, containers indistinguishable, and can a room be empty? Hold on a second. Each is large enough to hold up to 10 programmers. Okay, so if each is large enough to hold up to 10 programmers, then that's just a weird way of saying that you can't put all 11 programmers into the same room because they wouldn't fit. So saying that there are 11 programmers but the maximum capacity of any given room is 10 is another way of saying that you have to put at least 1 programmer in each room. Okay, so this is an objects distinguishable, containers indistinguishable, can't be empty set problem. And really, ultimately what this boils down to is, dude, I got these 11 programmers. How many ways are there to put these 11 programmers into 2 rooms such that no room is empty? Well, this is exactly what the Stirling numbers of the second kind were invented for. And in fact, the answer to this is just S11 too. The number of ways to place 11 programmers into 2 rooms. I think because 2 is such a small number, it's possible to just write the answer to this problem down. But anyway, there's no smart person right now to give me the common sense answer, so I'll just give that answer. Okay, someone comment on the YouTube video or something. Next, 11. A library has 4 identical display cases that are used to promote new acquisitions. Okay, this month the librarians wish to promote 9 books. They do not want any empty display cases. in how many ways can the books be displayed? Okay, so now Gossett isn't, I think, in my opinion, fully fleshed out this problem because a library has 4 identical display cases. By specifically referencing the display cases as being identical, I think Gossett wants us to somehow think that the display cases are, well, they're somehow exactly the same, but I don't know how a display case can be exactly the same because obviously the case has to be somewhere, and so you would think it would matter which books are in which case, but perhaps we are just preparing the display cases and then they're going to be put in who knows what locations. And that's actually not so unreasonable maybe. You're in the back room or something like that of the library and you are have brought the display cases back there and you are now just kind of like working on them or whatever, and then who knows where they're going to go. And so here we go. We have 9 books we want to promote. And if the display cases are indeed identical, then what we're really asking is how many ways are there to stick the 9 books? The 9 books are going to be all different and obviously visually distinct from each other into these 4 different boxes, the boxes of which can't be distinguished, and no box should be empty. Alright, so we're just putting 9 books into 4 piles. Well, once again, this is exactly what the Stirling numbers of the second kind count. The number of ways to place 9 distinguishable objects distinguishable, into 4 indistinguishable containers where no container is empty is precisely the definition of S94. And okay, hopefully that was clear that we're just answering these problems like with these numbers. And we'll go back and talk about how one can crank out these numbers. Well, we did it in the video, but in the earlier exercises we practiced that as well. Okay, so that's my answer. Now if you're being if you're a little bit unsatisfied with that, because you're like, come on man, a display case ultimately is going to be like a display case. And there are going to be 4 spots for these collections of books, and it's going to matter, which books are in which spot. Well, if that was your answer, then you could just take, so I'll just write like, alternate answer or something. You could just take that and then you multiply by 4 factorial, because then there are 4 factorial ways of ordering it. So S94 is the number of ways of deciding which books go with which other books, you might say. And then there would be 4 factorial times S94 ways of deciding which books go with which other books, and then also in which spot. Okay, good. We move on. Woo! I like, if we're doing this live, it's way more fun because people come up with all kinds of objections and I just like shoot them down and we have discussions. But anyway, that said, this is something maybe we can do this on our Zoom this week. Okay, 12! I have 7 new quarters that I wish to place into my 2 front pockets. I really don't care which pockets the coins end up in. In how many ways can I pocket the quarters? Alright, well I don't know what is it about the quarters them being new that should matter, but maybe we want to say that they're all brand new, so they're like from the same year or something like that, or the quarters are, visually identical or something like that, although they do all have little identifiers on them. Or maybe not. Maybe 2 quarters from the same year are actually indistinguishable. I can't remember. Anyway, we have 2 pockets, and then he says in a kind of an obscure way, I don't really care which pockets the coins end up in. How many ways can I pocket the quarters? Alright, so I think he's ultimately saying, how many ways can I put 7 quarters into 2 pockets? Not particularly caring which pocket it is, but just how many ways can I split up the quarters into pockets? Well, I guess what we have here is a objects indistinguishable. The quarters are all indistinguishable. That's my assumption I'm using to answer this problem. The containers are indistinguishable. Okay, this is a little less plausible. That we really wouldn't matter whether there's like 5 in the left and 2 in the right, or 2 in the left and 5 in the right. But that's what he seems to be saying. And then there's nothing that says you can't just put all the quarters in one pocket, and so this is the empty set situation. Okay, well, what do we have? We have 2 pockets, so we have 7 quarters and 2 pockets. So I guess the simplest way to do this is to sort of split it up into cases and to say, well, this is basically I either use both pockets or I don't. If I'm going to use both pockets, then this is just P7 too. It's the number of ways of writing 7 as a sum with exactly 2 sum ends. Or more straightforwardly, it's just the number of ways of splitting 7 up into 2 piles. But then you have to consider the case where we just put all the quarters in one pocket, which Gaussian wants to just count as just one case. So there it is. And this 1, if it makes you feel better to write this as P71, then that's kind of what that is as well, right? It's the number of ways of putting 7 objects into just one pile. So if you have the number of ways of putting 7 objects into one pile, the number of ways of putting 7 objects into 2 piles, then that's how you account for the fact that a pile could be, a pocket could be empty. Okay, I think these are pretty uncontroversial. Alright, let's keep going. 13. This one was also kind of exciting. An English professor has chosen 5 novels for a course in contemporary literature. Okay, so there are these 5 novels. Let's just call them novels, A, B, C, D, E. Okay, and you have to choose one. So, let's just assume that students do the homework that they were assigned to do. So each student must choose to write an analysis of at least one of the novels. Extra credit will be given for every additional analysis. Okay, well that's just a crazy extra twist, because now he's saying, look, you only have to do one, but if you do more than one, then you'll get extra credit. So, and if you do like 2 extra, then you get even more extra credit. And so really, this is like a kind of the curse and paradox of extra credit. Because if, grades are just some zero-sum game, fight to the death finish where you're just competing against your peers for the highest possible grade, then even though you only have to do one, if you only do one and everyone else does all these extra credits, then, they're going to get really good grades and maybe you won't. So they might as well have just said, well, I guess I'll stop my commentary there. One can do either 1, 2, 3, 4, or even possibly all 5 reports. And if we care, as we should I think, which report is being done, which book is being read and having a report written on it, then there's kind of a lot of cases I think. Well, let's actually just finish reading the question. There are 6 students enrolled in the class, so nice small class. Give a numeric count of the number of ways the students can submit reports. What are the total number of ways this whole thing can play out? If you have 6 kids in your class, you assign them to do 1 of 5 novels, and you tell them that they'll receive additional points for each extra credit assignment. What are all the possible submissions that you might receive? Well, let's just consider a single student. A single student can either do a book report on just A, or just B, or just C, or just D, or just E, or A and B, and A and C, and A and D, and A and E, or A, B, and C, A, B, C, D. In other words, all possible subsets of A, B, C, D are possible. And so there are in fact 31 possible ways for someone to write a report on some of those 5 books. That's for one student. So the first student has 31 options, the second student has 32 options, the third student has 31 options, etc. And so there are in fact 31 to the 6th possible ways for these assignments to be done. And if you want to include the possibility that a student just doesn't answer any of their emails or go on Canvas and doesn't submit any work at all, then now you're just including the option, the empty set subset. So that would be like 32 to the 6th possibilities. Okay, so that was pretty exciting. Oh, what is this? I guess this is a, I don't even know what this is. This is just a math problem. Oh, I guess this is that last one. It's the containers. I don't even know what I'm doing. I guess, well, whatever. Let's not try to write this as an occupancy problem. Let's just leave it at that. 14. Right, 14. Exciting. Mei Ling received 3 identical laundry baskets as high school graduation presents. Okay, so just some big white basket or whatever. She has brought all 3 to college. If she has 20 pieces of laundry, in how many ways can she stuff the bags with all 20 pieces of dirty laundry? Okay, I like this problem because laundry baskets are so sort of just amorphous and you're constantly moving them and carrying them around, do laundry back and forth. that you definitely don't think of them as being fixed in any one particular place. And so laundry baskets might as well just be piles, right? How many ways can we split the 20 different pieces of laundry up into 3 piles? Or putting them into 3 laundry baskets is how the question phrases it. Okay, this is kind of exciting because we assume that the individual pieces of clothing are all distinguishable from each other. They're 20 pieces of clothing. They're like, cool like Space Monkey shirts and things like that you can tell apart. And so what we have are some objects distinguishable, containers indistinguishable, and I think that also the laundry baskets can be empty. Because there's nothing that says that she has to use all 3, right? She could put all her laundry into just one bag, for example. Okay, and so this is the case where we say, okay, let's do it by cases. Suppose she uses just one. Suppose she uses all 3 laundry baskets. Well, if she uses all 3 laundry baskets, then this problem reduces to how many ways can these 20 distinguishable pieces of laundry be split up into 3 different piles, and that is S23. That's again what we created the Stirling numbers of the second kind for, the number of ways of distributing 20 distinguishable pieces of laundry up into 3 different piles. But what if she only uses 2 of the 3 laundry baskets? Well, then that would be S22. If she just uses 1 laundry basket, then that would be S21, which is of course just 1, because there's only 1 way, but okay. Good. That was great. Okay, bunch more. 15 says, 15 people are going to attend a picnic. Shirley is packing 1 ham and cheese sandwich for each of these people. What a nice person Shirley is. She will carry the sandwiches in all 3 of her red and white checkered picnic baskets. Classic gossip. Alright, how many ways can Shirley bring the sandwiches to the picnic? Okay, well, the objects, the ham and cheese sandwiches, are all presumably identical. She just made 15 ham and cheese sandwiches. They're all basically the same. Let's accept that. The containers also seem to be indistinguishable because there was just reference to 3 checkered picnic baskets, and that's it. In all 3. Okay, she will carry the sandwiches in all 3 of her baskets, which seems to indicate that no basket is going to be empty. That would be kind of silly. Otherwise, then you wouldn't bring it at all. So basically, this basically says, how can I put these ham and cheese sandwiches up into piles, basically? And this is exactly what we invented the partition numbers for. This is just P23. Okay. No, not 20. 15. Sorry, P15. There are 15 ham and cheese sandwiches. Okay. 16. What does 16 say? Jeff just went shopping and bought his parents an anniversary present consisting of 8 blue towels. Presumably these are 8 identical blue towels. The cashier told him that she had 4 white bags available for carrying the towels home. And once again, the bags are all jostling in and amongst each other, so there's nothing special about any one particular given bag. In how many ways can Jeff bring his towels home? Assuming that Jeff does not have to use all the bags. Okay, so this is a classic situation where maybe they give you more bags than you need, and so you don't necessarily have to use all the bags. So what do we have? We have 8 towels, all exactly the same, 4 bags, all exactly the same, and we want to know how many ways are there to put these 8 towels into these 4 bags where we don't necessarily use all the bags. So this is objects indistinguishable, containers indistinguishable, and it seems as if Gossip's even telling us you don't have to use all the bags, so empty containers are permitted. Okay, well, here we are splitting up towels into piles, but we're splitting them up into an unknown number of piles. And so it's possible that we split the 8 towels up into 4 piles, and there are P8 4 ways to do that. That's assuming that we're using all the bags. But if we only end up using 3 of the bags, then it's P8 3. And if we only end up using 2 of the bags,
Then it's P82, how many ways of splitting up 8 into 2 piles. And finally, P81 is the number of ways of doing with just one bag. And I guess we discussed in the video that this can be written more succinctly as P12-4. Oh boy. And what is the reason for that again? The reason for that again is kind of subtle, and I guess we're going to sort of do it more carefully later. So maybe I'll just leave it for now. Maybe I'll just leave it for now. One way of thinking about this is if it turns out by some just wild twist that these white bags that the cashier gave Jeff, in fact, these white bags are themselves blue towels. Okay, don't ask how that could be, but just suppose that in disguise, each of these, they seem to be white bags, but after an hour or something, their apparent white bagness fades, and in fact, what you have is a towel. Well then, this is so dumb, but this is good math. In fact, the number of ways to split the 8 towels up into 4 bags, well, you didn't really have 8 towels and 4 bags. You actually had 12 towels. And because the bags are the bags, then you were guaranteed to be having 4 piles of towels. And so that's some sort of silly but maybe good way of seeing why this is P12-4. Okay, but more on that later. We run out of space. Let me erase this. Okay. Good. And yeah. Going to 17. 17. 17 says, suppose that you are going to design 6 blue t-shirts. Oh man. Okay, so you have 6 t-shirts. Great. You have 9 pictures that can be ironed onto the t-shirts. You have 9 iron-ons. Okay, now, it's come to my attention from teaching this class that people don't know what iron-ons are, and that's because this is like, the 21st century where you have like the internet and all that kind of stuff, and once upon a time, nowadays if you want to like make a cool, Wallops t-shirt and give it to like 20 of your friends, you just go on the internet and the whole thing is, at your doorstep in a couple days. But once upon a time, if you were like in 4th grade and you were on some like soccer team and everyone in the team wanted to have the same t-shirt, you would buy generic t-shirts and then you would buy these iron-on patches and you would just iron them on. That's how you got custom-made t-shirts. There weren't all these companies just mass-producing t-shirts for you on demand, or at least not so easily. Here we have these iron-ons. The point of this story is that once you have an iron-on, what are these iron-ons, by the way? Gossett's going to tell us, of course. There's a lion, a cat, a flower, a heart, a moon, a star, a person, a palm tree, and a dolphin. Point is, there are 9 separate pictures, and once you use one of these iron-ons, it's used up. So you have just 9 of these things, and you iron it on, and then it's done. Okay, how many ways can the t-shirts be created, assuming there are no boundaries concerning the number of pictures to be placed on each t-shirt? Okay, so I'm going to make a couple of assumptions here. The shirts are all, in their initial stage, completely indistinguishable from each other. They're just plain blue shirts. And we're just making the t-shirts. We don't know who's getting which t-shirt. And there are 9 of these pictures. The pictures are all different from each other. And there's nothing that says that you need to put at least 1 picture on each shirt. You could put all 9 of these iron-ons on 1 shirt. And we also have to assume that when he says how many ways can the t-shirts be created, that we are not taking into consideration the visual arrangement of the iron-ons on a shirt. we will consider it, we will judge the shirts by the presence of a particular design on that shirt or not. Okay, so having discussed all of that, I think it's now clear that the question really is, dude, how many ways can you distribute these 9 iron-ons to the 6 various shirts in some kind of a way? And so what we have is an objects distinguishable, containers indistinguishable, and I think the empty set is certainly permitted. Well, this is going to involve Stirling numbers. Once again, we could put all the, well, it's weird to start at the beginning, but we could put all the iron-ons on one shirt. Well, that would be S91. We could put all the iron-ons on 2 shirts, so distribute the 9 designs onto 2 shirts, or onto 3 shirts, or etc., all the way up to using all 6 shirts. This would be the number of ways of spreading the 9 designs onto the 6 into 6 different, putting them into 6 different piles, or putting them onto 6 different t-shirts. Okay, so this whole thing is the sum from I equals 1 to 6 of S9I is one way of putting this problem. Okay, good. A couple more. 18. Suppose you're the boss of a small company. You have 3 distinct jobs that need to be completed next week by people on your staff. Stuffing envelopes, copying files. So stuffing envelopes, copying files, and typing. These are the 3 jobs. There are 7 employees who will each be assigned one of the jobs. Okay? Now you have 7 employees, and the employees are all distinguishable from each other. At least one employee must be assigned to each task. In how many ways can you assign the jobs? Okay, well, if we want to consider all the possible ways to assign these jobs to an employee, you might think, well, why don't I just go through each employee one at a time and to assign them one of the 3 jobs, and then that would be 3 options for the first employee, 3 options for the second, so that would be 3 to the 7th. But that would be wrong because this would involve cases in which you failed to assign at least one employee one of these tasks. And so that's sort of not the way to go about this. The way to go about this instead is to think of the tasks as being containers, and think of the employees as being objects that we're placing into those containers. And based on the way we've developed partition numbers and Stirling numbers of the second kind, it's easier to temporarily consider those containers to be indistinguishable. And so what we do is we sort of imagine that there are these 3 containers totally indistinguishable, and how many ways are there to put these 7 people into these 3 containers? Well, that is S73 exactly, right? S73 is the number of ways to distribute 7 employees up into 3 different piles. But now that we've put them in those piles, it doesn't just matter which employees are with which other employees. It also matters what they're being assigned to do. And so